hi everyone, welcome back. First is an announcement that we will have midterm exam in the week of April 8th to 15th, and then you will have actually an entire weekend to finish the midterm. The midterm, of course, is take home, and it's open book with internet access. That means you can look at lecture notes, look at your homework, also look at Wikipedia and other resources. The only thing that you cannot do is to search for the same problems. And to be honest, that's not even a thing because you wouldn't find identical problems on the internet. And then the exam would be posted on the Colab on April 8th, and then you will be asked to submit your solution before April 15th. Okay. And about the the content of the midterm, it'll be something quite straightforward, almost identical to homework and your lecture notes. And the idea, well, the purpose of this midterm is just to spread out the risk, right? Like I don't want just one final exam to decide, okay, your score. And for those of you who are auditing this class, I encourage you to take the exam as well, because the policy is that if you do well, if you're satisfied with your exam result, and then next year or the next time that you actually officially enroll in this class, you don't have to take the exam anymore. You don't even have to take the class. We can use the exam score you have at this semester as your final grade. Okay, any questions? Okay, good. So today we will continue our discussion of third-order nonlinearity effect. Sorry. And last time we learned that a very critical difference between third-order nonlinear effect and second-order nonlinear effect is that there are certain phenomena that doesn't require phase matching condition, or the phase matching condition is not that significant. And an example we show is that for a single frequency input into a Chi3 media, what you will see is that the refraction index of that media will be modulated by the intensity of your input line, and this is called a Kerr effect. And we prove it, okay, with our nonlinear optics framework under a single frequency assumption. Okay, we didn't put multiple frequency components into our calculation. So here today, what we're going to show is that, okay, what will happen if there's more than one frequency that's input into the Chi3 media, okay? And this is Kerr effect. Also, when it's single frequency, it's called self-phase modulation. Okay, we have learned this in the previous semester, previous class. And now the way that we derive this, there are multiple different ways. So in this class, we kind of try to unify everything in the same framework, that is the nonlinear polarization and nonlinear equation. And but before we do that, we can kind of guess what would the result look like, right? Suppose we still have a Kerr effect, right? The Kerr effect still look like this. So possibility A is that, okay, the refraction index, when you have multiple frequency components, the refraction index of frequency omega is modulated by the intensity of the components of omega. All right, so the intensity of light at omega modulates the refraction index of light at omega. That's one option, okay? That's a reasonable guess. And then the second possible option would be the time, okay, the refraction index at time t is modulated by the intensity of light at time t. Okay, and this is kind of usually the way that people approach problem is that either in frequency domain or time domain, right? So very intuitively, you can see that A is wrong. Okay, this is wrong. It is wrong because in nonlinear equation we know that, right? If you write down the nonlinear polarization, third order, okay, it would be I think it's epsilon chi 3. Right. We know that because it's nonlinear, well, mathematically it's a nonlinear term, so that the different frequencies will be mixed together. And the light intensity at one frequency should be able to influence the refraction index, or should be able to influence the output of light at a different frequency, right? So the guess, like option A, right? The guess A, that the frequency, each frequency handle its own business, it's in sharp contradiction with the nonlinear term here. Okay, so today we are going to, well, I think maybe not today, but at least on Wednesday we'll finish the proof. Okay, that by using the nonlinear equation we developed a few classes before, that we can show that, okay, the refraction index of light, okay, is modulated by the intensity of light at time t through the Curry effect, or third order nonlinear effect. Okay, so let's first, well, the first thing we can do, of course, as any nonlinear problem, is just to write down the nonlinear equation, right? So we already have the nonlinear polarization here. Again, we neglect the electrical field polarization. We assume everything is at the same polarization for simplicity. Okay, and if you turn to page 10, that we'll see our very familiar equation for nonlinear optics. That were originally structured in frequency domain. Right, it's structured in frequency domain. Okay, and of course we will have the light, because the light will have many different frequency components. We can write it down as okay. So this is the starting point, again, very similar to any nonlinear problem. The only difference is that the nonlinear polarization now is chi 3, is e to the third. Okay. Now let's look at what e to the third will look like. Right. And here, because you guys already have enough experience with calculating nonlinear polarization, so here I will not start with example like one frequency, two frequency. Okay, instead we'll start with the sum here, J. Okay, assuming there are there are a lot of frequency that you will not write them down one by one. Okay. So e to the third. The way that we can approach this polynomial is that you can write down E, okay, as of course E times E. Right. And for each E, inside each electrical field, you will have a negative frequency term, okay, and then it's complex conjugate, right? So the way that we can write it down, like symbolically, is we can write down E to the J1, right? This is the first electrical field, okay, the sum is this part, okay, it's J1. And plus, its complex conjugate, we can write down as L1 and label conjugate here, okay? This is just a label, right? You understand here, E sum of J1 meaning this part, and you change the subindex from J to J1, okay? Sigma L1 conjugate means the sum of this, you change J to L1 and then do a complex conjugate on all the terms, okay? And this represents all the terms that is included in E, okay? And the reason that we need to do this is because these two different, the conjugate and, the negative frequency components and its conjugate, okay, when you start to do the polynomial, okay, is very different, right? Because suppose, okay, 3 minus components, if they multiply together, that give you third harmonic generation, which is something that we actually don't want, okay? So that's why we write them in separately, okay? And you can do the same thing for J2, L2. Right, that's how we label the second E, right? And then the same for the third E. And pay attention here is that J1, J2, J3, they don't have to equal to each other, right? They don't have to equal to each other. They're just labels. It indicate, okay, if you have a E, okay, just indicate which, for example, if you have E, J1, okay, it indicate this term is coming from the first E, okay? That's all it does. Any questions here? Okay. Now, then here we need to decide, okay, to remove certain terms. And the reason is that if we look at the form of, Kerr effect, right? What we have said before is that the special thing about Kerr effect is that the frequency, okay, it generate is actually, at least for single frequency input, okay, the nonlinear polarization will return a term that at the same frequency, okay? So here is that it's the same thing. Here is that not identical but similar thing is that we only care about the term, okay, that has a frequency that's very close to your input, right? For example, third harmonic generation, we don't care about it, okay? So that being said, it means any term that comes from here, 1, J2, J3, right? First one, second one, third one. When they multiply together, you can see that their frequency components, if you write it down here, would be minus I omega J1 plus omega J2 plus omega J3, right? So this frequency would be much larger than your input frequency, right? If it's J1 equal J2 equal J3, then it's third harmonic generation. If they're not equal, then it's 3 waves summed together to generate a new wave. And we have already know, okay, from previous experience, process like this will require phase matching condition, okay? Require phase matching condition. So here what we can do is that we can say that we ignore these terms. because the difficulty of achieving phase matching condition, and also because the frequency is very different from your input, and it's unlikely to create a modulation of your reflection index. Okay, and what's also ignored is the complex conjugate of it. Okay, so both the electrical field components and then, well, both the negative frequency component and its complex conjugate are ignored. Okay, any questions here? Okay, if no, then we can now try to write down, okay, what what the term will look like here, the remaining term will look like here. Okay, so if you look at it, the option of 3 are both the negative frequency components. Okay, this term is ignored. Also, the 3 that are the conjugate of it are also ignored. So what it means is that in this polynomial, that you have to have 2. You either have to have 2. Okay. What label should I use? Okay, let's use mu1. You have to have 2 negative frequency components and then multiplex with the 3rd complex conjugate components, or the reverse, right? Right, or the reverse. Okay, and again here mu1, mu2 at a prime here, meaning that they doesn't have to equal each other. Right, these are the remaining term when you rule out all 3 frequency are negative and all 3 frequency are positive. Okay, these are the remaining terms. Okay, any questions so far? Okay, and if we keep looking into this, what this will give you, okay, here why we use mu1, mu2, mu3 instead of j1, j2, j3. Okay, the reason we do that is that this positive term, this negative frequency term, can come from j1, j2, or j3. Right, so just to write it without losing generosity, we define a new index as mu1, mu2. Okay, mu1, mu2. Of course, you can see later. Okay, there will be a factor of 3 here, because this mu1 can come from either 3. Okay, it can come from either one of these. Right, so there are 3 options. Okay, so later we will go into the details here. Okay. So if you look at this form, then what it will give you is it will give you minus I omega mu1 plus omega mu2 minus omega mu3. Right, the term you have. Okay, and then plus I k mu1 plus k mu2 minus k mu3. Right. So this term, okay, when you have 2 negative frequency components multiplex with one of the conjugate, what you end up with is still a negative frequency component. Right. You have 2 frequency plus together and then minus the 3rd frequency. Right, so imagine if this is mu1, mu2, mu3 equal to each other, then what you get is omega plus omega minus omega. So you're arriving back at the same frequency, right? And if you're, let's say if this is omega mu1 and this is omega mu2, and then so if this plus this minus this will actually give you So what it is that this is the critical takeaway here. Okay, is that this is a negative frequency components that's would go in here and then balance this term. Okay, then balance this term because they all have the negative frequency component. Okay, and this term, as you can see, it looks like the complex conjugate of the first term. Okay, so when you go in and do the calculation, you will see, okay, all of them are just have a negative. All of them are just conjugate. Okay, so in this specific calculation, we can focus on. We can just focus on this one. Right. And then also we can, since we already separate the negative frequency components and its conjugate, okay, then it's okay to just use the complex form of the electrical field. Okay, so you have to be very careful here. Like every time when you do nonlinear polarization calculation, right? It's if you throw away complex conjugate, sometimes it will cause problem unless you are absolutely sure. Okay, this is something okay to do. Okay. Okay, so let's see how we can rearrange the index here. Okay, now suppose the E3. Okay, suppose one of the frequency components it will generate is something called omega mu. Right, omega mu. And omega mu. And then the way that you can generate omega mu, let's say it's equal to omega J1 plus omega J2 minus omega mu1 plus omega mu2 minus omega mu3. Right, so now our job is to count how many terms from here can actually create these frequency components. Right, because eventually if you look at this nonlinear equation, you have to match a specific frequency components on the left-hand side to the right-hand side. Right, so it's important when you pick out a frequency, you have to know, okay, how many terms you have on the right. Okay, then you can write down the complete equations. So now the way you can think about it is that, okay, if we know in the system omega mu has to come from this mu1 plus mu2 minus mu3 has to come from this frequency combination, then it's very clear that you have three options, right? You have three options. First is that let me see here. First is that J1 equal mu1, J2 equal mu2, and L3 equal mu3. Right, you pick up omega mu1 is from the first term, omega mu2 is from the second term, omega mu3 is from this term. Right, it's in this order, so you have one term, okay, from this order. And then you have another choice, right? Of course, you can have L3. Okay, if you look at it, the see here. I'm not sure my note is correct, but I could have missed a two factor here. But anyway, let's keep on going here. The second one is that if you look at it, the critical factor here is actually the mu3, right? Because mu3 has a conjugate. And mu1, mu2, okay, you can choose either one, right? So the other one would be L2 equal mu3, okay? L2 come from here. Mu3 coming from this one. and then the mu1, mu2, okay, come from this one and this one. Okay, so you can keep having J1 as mu1, J2 as mu3. Okay, J3 as mu3. J3 as mu2. Okay, and of course for every option you can see that you can switch J1 and J2. Right, you can switch J1 and J2 because it's always the same as mu1 plus mu2. Okay, and then the third is that if you pick mu3 to come from L1, right, the conjugate term from L1. So you have L1 equal mu3. Okay, and then we just follow the simple order J2 equal mu2, so equal mu1. And then J3 equal mu2. Okay, and then this can all flip, right, the first three terms here. Okay, then now how do we write down this term now? Okay, so what we can do here is that we can write it down as the term that corresponding to mu, okay, is that, let's see here, is epsilon chi3, okay, mu1, mu2, mu3, and then we enforce omega mu1 plus omega mu2 minus omega 3 equals omega mu, right, if you select the mu, right? And then E mu1, E mu2 times E mu3, complex conjugate, and then let's just put it here. Sorry about the writing here. Exponential minus I, omega mu1 plus omega mu2 minus omega mu3 t plus I k mu1 plus k mu2 minus k mu3. Okay, so it's sum over all possible mu1, mu2, mu3 that can create this frequency. And here that's the critical part, okay? The factor here, if you look at note page 10 or page 11, the factor here is 3, okay? It corresponds to these 3 different combinations, right? You have 3, for each omega 1, omega 2, omega 3, you have 3 terms coming from here. And the question is why it's not 6, right? We say that J1, J2 can always flip, right? Why it's not 6? The reason is that not only J1, J2 can flip, you can actually equivalently, you can flip mu1, mu2, right? Flipping J1, J2 is the same as flipping mu1, mu2. And that will be included in the sum, right? If mu1 is 1, mu2 is 2, you will also sum the situation where mu1 is 2, mu2 is 1. Right? So as long as you don't impose any restrictions on this sum, okay, this mu1, mu2, mu3 free sum actually already include the case where you flip J1, J2. Okay, so that's why the coefficient here is 3 instead of 6. Okay, so this one have to be extra careful. Okay. So now we arrive. So this is the nonlinear polarization here, P and L, of the term corresponding to omega mu. Okay. So now we arrive at, let's see, where should we put it? It's a very long equation. I should plan this better. Let's see. Let's write it here. Okay, let's use 3 lines here. So on the left-hand side, you will have the equation of your muth component. Okay. Right, that's the muth frequency components, and mu can be any number, right, you assign to your frequency. And then this equal to this term here, and of course you need to do twice the time differential, right? That will give you minus omega mu square, right? Because omega mu1, mu2 minus mu3 is omega mu. Okay, and then epsilon, okay, time with this, so you have minus 3 mu naught epsilon naught, okay, omega mu square and chi 3. Okay, these are all the coefficients in the front. And then sum mu1, mu2, mu3. Okay, and then this term. Okay, so E mu1, E mu2, E mu3 conjugate exponential minus I. I'm not sure if my handwriting is too small for you to see on the screen. If it is, you can turn to page 12. The very first line is actually this equation. And plus, right? This term is here, and then it has a complex conjugate, right? This term, so plus a complex conjugate. Okay, so this is the this is the nonlinear equation, complete nonlinear equation you can use for third-order nonlinear effect. It's very scary, and if you have any sense, okay, you'll see the number of terms here. Suppose you include n frequency components, and the number of terms here is n to the third. Okay, it's a cubic term. So even if you just include 10 frequency components, you will have 1,000 terms. Okay, so actually there's a, well, this is actually, there's a paper 10 years ago. Okay, this is still quite modern. Paper 10 years ago saying that you should not calculate this in frequency domain. Okay, that's actually why in the, let me see the time. That is actually why we want to convert it into time domain. Okay, in time domain, you will see, okay, it is, in time domain, what it does is later we'll see that the critical difference between frequency domain and time domain is actually, of course, they're connected by Fourier transform. Okay, it's just when you do Fourier transform, these terms, okay, multiply together in frequency and then give you a new frequency, okay, will actually cluster into multiply in time. Okay, and then that would be much easier to solve. Okay, much easier to solve. So here, it's important to know, okay, where the equation come from, and then so that we work in a very unified mathematical framework. And then the second thing is starting from here, we'll introduce two very simple situations. Okay, just for example, n equal 1, that's we already solved it last time. Okay. N equal 1 meaning that there's only one frequency. Okay, that one we already solved. And then next we'll look at n equal 2. Okay, n equal 2 is like you have two input and what will happen. Okay, and then I think I can erase this. Any questions so far? And by no means, okay, like in nowhere in the exam or homework you will be asked to solve something like this. Okay, it's not human. Okay, so we're not going to do that. And if you're interested in how to solve this numerically, okay, there are several papers about it. We won't talk about this in detail, but if you're interested, you know, I can answer that later. Okay. Now, the simplest case is one frequency components. We already solved that. And now let's look at two frequency. Okay, so two frequency input from the left-hand side. Okay, omega 1, omega 2. So there are two problems we need to consider here. One is that what happened to let's see, okay, this one. Okay, what happened to these two frequency components? Right, are they modulated? Is the refraction index of them modulated? Okay, in any sense, right? So it's like you have input and what is the output? And the second part of the question is that because we now know, okay, this is a very scary thing, okay, whether there's new frequency being created. Right, those are two part of questions. Okay, and the first, well, we can try to answer the first question. Well, we can answer both questions today. Okay, so so if you look at it, if you want to know what it does, okay, what this nonlinear polarization does to omega 1 components, then what we should do, right, is to solve the equation where mu equal 1, right? That gives us the components of E1, right, omega 1, and then you calculate this, right? So it looks like scary, but remember there's only two components, right? So mu1, all the mu can only equal to 1 or 2. Right, so to come out as omega 1, right, when mu equal 1, let's put it this way. Okay, there are only, well, as this equation indicates, right, omega mu1 plus omega mu2 minus omega mu3. Right, there are not many options here. There are not many options here. The first one is that mu1 equal mu2 equal mu3 equal 1. Right, so frequency components omega 1 plus omega 1 minus omega 1. Right, and these two cancel and you are left with omega 1. Okay, so if you choose this mu1, mu2, mu3, you will get a component that has a frequency of omega 1. Okay, and then there's only one of them. The reason is that you cannot switch. Well, it doesn't make any sense to switch mu1, mu2, mu3, right? Because they're all equal to each other. Okay, so there's only one of these terms in the sum. And the second one is that you can see here is that as long as I keep mu1 equal to 1, I can let mu2, mu3, as long as mu2 and mu3 equal to each other, they will cancel anyway. Right? It doesn't even matter what mu2, mu3 is. As long as they're equal to each other, these two terms will cancel each other. So because here there are only two frequency components, so we will let mu2 equal mu3 equal to 2. Right? So it's a second frequency component, omega 2 minus omega 2 equals 0, and then you're left with omega 1. And of course, you can do the same thing by assigning omega mu2 equal 1. Okay, this one is omega 1. And then mu1 and mu3, they cancel each other. Okay, so these are three different situations. Okay, three different situations. And now if you look at the terms here now, so, okay, and we can kind of, well, we put the coefficient here in the front. Okay, so the first term, mu1, mu2, mu3, they all add up together. They're all 1. Okay, so you have E1 times E1 times E1 conjugate, right? And then here we already know that mu2, mu3, they cancel each other. Mu2, mu3, they cancel each other. So it's E minus I omega 1t plus I k1z, right? This is the term of cos u plus complex conjugate. And if you take a look at this, E1 times E1 conjugate is just the amplitude square, right? So you can simply modify this term into E1 square E1, okay? And if you remember this, this is just the self-phase modulation, right? The amplitude of E1 modulate the create a nonlinear polarization at frequency omega 1, okay, itself, and then later when you combine this into using this, right, D equal to epsilon r E plus P, right? So later, because E1 has the same frequency as E, this nonlinear polarization, so we can move this term from P here into here, and then move this part as a coefficient into epsilon r, and that will give you refraction index change. Okay, this is something we talked about in the last semester, last class, so I'm not going to repeat it. And if you look at here, and okay, this term is E1, okay, times E2 times E2 conjugate, okay, and the frequency component term is the same. Okay, and the third term here is, this is 2. Omega 1, mu 1 is 2, okay, so E2 times E1 times E2 conjugate. Okay, so if you look at it closely, what you will see is E2 conjugate. This is just E2 amplitude square, right? So if you write it down in the same format, so it's E2. And then the same apply to this one, E2 conjugate, right? So these two terms are exactly the same, so that you will actually add a factor of 2 here, and then erase this 2. Right, this factor of 2 is actually the case when we discussed before here, saying that J1, J2, they can flip, right? And that will give you a factor of 2. And so in total, when you multiply 3 and 2, it will give you a 6, right? So that's previously how we we count those states. Okay, then now this becomes very clear now. Okay, you will see that from D, the displacement field equal epsilon r E linear plus P, okay, and for the Mills frequency component, sorry, for mu equal 1 now, okay, for frequency component 1, what you will have is that you will have epsilon r E1, okay, and this E1 actually contains Z and T, okay, frequency and time, okay, plus this is the nonlinear polarization that, okay, this is represent the nonlinear polarization of P, right, that has a frequency component omega 1. And all this coefficient, we can just assign it, for example, a gamma here. Okay, just represent the coefficient. And inside you have E1 squared plus 2 E2 squared times E1. Okay. And you can very conveniently combine them. Okay, and then as you know, epsilon r equal to n squared, right? So you know that the fact that you have a polarization that is at the same frequency as your input will give you modulation of the frequency. And this part is the omega 1 components modulate omega 1 itself, right? So this is called self-phase modulation. Self-phase modulation. And this part, you see, is the frequency component from E2, omega 2, that actually modulate omega 1, right? Modulate the refraction index of omega 1. So this is called cross-phase modulation. Cross-phase modulation. Right? Cross the term, you use the other light to control this light. Okay. And the factor of 2, okay, this is important. Okay, there's a factor of 2. This is very critical. That comes from the fact that you can have two different, you can have two orders from mu1, mu2, mu3 that can create this cross-phase modulation. Okay, so that there's a factor of 2 here. Okay, and this factor can actually be measured in experiment. Okay, I can give you a very simple example here. See here. Okay, suppose I guess you guys all know optical resonators, like a ring resonator. Okay, light can go in and then circulate, and then you would have a refraction. You actually have a resonance frequency. Okay, resonance frequency, and something that you can actually show people, you can actually measure in the experiment is that, let's see, if you have a clockwise pump, okay, you have a pump power sending in here, okay, circulate like this, and this will change the refraction index and of course change the resonance frequency, right? Okay, it will change it. But what you will see is that it will also change the refraction index of the counterclockwise direction, right? Because for the counterclockwise direction, your clockwise light act as a cross-phase modulation term, right? And then the refraction index change should be twice as large as the clockwise term. Okay, so you can actually measure in the experiment is that when you send in a clockwise light, okay, it will create a splitting, or it will lift the degeneracy of the clockwise and counterclockwise light in your resonator. Okay, for the clockwise, it will go through a self-phase modulation. Okay, that's this term, and shift it by a certain amount. And then for counterclockwise term, it's a cross-phase modulation, and then it will go twice. Okay, it will go twice. And this actually can be measured in experiment. Okay, and people have actually measured it many times. And then there's other system you can measure this factor of 2 here. And something that I have to emphasize here is that when, probably none of you will actually do this experiment, but if you do measure phase modulation or refraction index change, right, through the self-phase modulation or cross-phase modulation, something you have to keep in mind is that when you send in light into a media, That's not the only thing you can change the refraction index. Okay, if you actually go into my lab and try to do this experiment, you will not see this effect. Why? It's because the resonator I use in my lab, the drift will come from thermal. The light coming here will actually heat up the resonator, and then the thermal drift will be huge. And then your current drift will be very small. So unless you can do a very precise measurement, otherwise you wouldn't see this effect. Okay, and so in fact, in most systems, you will first see the thermal change in your refraction index, then you will see the current change. And how do you distinguish these two? Okay, the very easy way in experiment is that to keep in mind is that this current effect is instantaneous, right? It's the response from your electron inside your atom. Okay, so that's very, very fast, happen on femtosecond scale. The thermal drift, on the other hand, is very slow, right? Because thermal is actually the vibration of the atoms, right? It's much, much larger than electrons, so it's actually happen very slow. So to do this experiment, if you really want to see this effect, what you can do is that you can turn on the light and shut down the light very quickly, and you measure the instantaneous response from the resonator. Okay, that you will see current effect. And if you wait long enough to measure the response, then you will see the thermal effect. You see the light, you see the resonator being heat up and drift this way, and then cool down, coming back. Okay. Okay, very good. And okay, so this part is cross-phase modulation, self-phase modulation. Okay, and then any questions? If not, we can move on to the second part. The second part is that if you have two frequency input, right? Omega 1, omega 2. Would it generate new frequency components? Right? Would you generate new frequency at the output port? And this one can be kind of straightforward, right? You just count the combination and then see, okay, what the frequency here will look like. And very obviously, there can be one frequency that's omega 1 plus omega 1 minus omega 2, right? You let mu1 equals 1, mu2 equals 1, mu3 equals 2, right? Give you this. And apparently this doesn't equal to omega 1 or omega 2, right? This is a new frequency components. And if you look at it, what it is that, okay, yeah, actually it's omega 1 plus, well, the way that you can look at it is this. Okay, it's omega 1 plus the difference between omega 1 and omega 2. Right, and then because we know omega 2 is larger than, well, in this case we assume omega 2 is larger than omega 1, so you can kind of, I think you can kind of assign, by definition, okay, define, okay, a delta, right? That's a frequency difference between omega 2 and omega 1, okay? So here then, by this definition, there will be omega 1 minus delta, right? Delta is larger than 0, okay, in this situation. Okay. Then what it is that, okay, where is this new frequency? This new frequency will be sitting here, right? Okay, it's smaller than omega 1 by the amount of delta, by the amount of the difference between omega 2 and omega 1, right? So it's like an equidistance, okay? And you can also generate other frequency components, for example, omega 2 plus omega 2 minus omega 1, right? It's mu1 equal 2, mu2 equal 2, mu3 equal 1, right? And if you look at it, what this is, it's just omega 2 plus delta. right? Omega 2 plus delta. So this is omega prime. Okay. So again, this is equidistance, right? So the distance between omega prime and omega 1 is the same as the frequency difference between omega 1 and omega 2 is the same as difference as omega 2 and omega prime, double prime, right? And then when you create these new frequency components, okay, you can keep using them to create a new frequency component, right? You can just plug them back in here, and then you can go through all this calculation, and what you will see is that the new frequency, okay, generated by this will all have, okay, are all in line, okay, and then their frequency separation is always delta with its neighbor, okay? It's always delta with its neighbor. And this is kind of something very obvious. It's because what you're doing here is just a simple combination of the frequency, right? And if the frequency difference is delta, you can think about it, if this is a fundamental difference, the smallest difference between two frequencies, then adding frequency and subtracting frequency will not create a frequency difference smaller than this. Okay, it will just create multiple integer times this difference. Okay, so this is kind of a natural result, okay, from this, sum and minus. Okay, and laser light with their frequency, well, this is called equidistance. Okay, frequency equidistance. Their frequency equally distance with each other is called frequency cone. Okay, this is called frequency cone. It's a weird name. Okay, actually, I think like when people say frequency, if you try to Google, okay, laser comb, what you will see is some hair treatment, okay, given by doctors to treat certain symptoms. And the better way to understand this is actually it should be like a frequency ruler, right? You can think about these laser lines as the grid, as a grid on a ruler, right? And then there's a marker, okay, on the ruler, and the comb, okay, is actually a ruler on the frequency domain. Okay, and the effect, okay, this effect, what is called when you generate new frequency, let's see, not, okay, so new frequency from this chi3, okay, not harmonic, not sum, okay, you know what I'm talking about, this frequency nearby, okay. This is called four-wave mixing. Okay, four-wave mixing. You see, okay, where the four-wave come from? Okay, where exactly does the four-wave come from? You see, if in the frequency domain, right, what you have is omega mu equal to omega mu 1 plus omega mu 2 minus omega mu 3. Right? In another way, if you rearrange the term, you will see omega mu plus omega mu 3 equal to omega mu 1 plus omega mu 2. So if you look at the process on the photon level, that what really happened is that this process corresponds to you have a photon coming in at frequency omega 1, okay? And then you have another photon come in at frequency omega 2, okay? And then through the nonlinear interaction with the media, you will generate omega 3 photon and then an omega mu photon. Okay, you generate omega mu photon. So this is, mu 1, mu 2, mu 3, and mu. Okay, so this effect in total, evolve can accommodate at most, okay, 4 frequency components, right? 4 waves at different frequency. So this is called 4-wave mixing. Okay, this effect is called 4-wave mixing. And now you have a sense, okay, you have a sense that both the cell phase modulation, cross phase modulation, okay, and then 4-wave mixing, okay, they all come from the third order nonlinear effect, okay, from this term, third order nonlinear effect. But what they do is slightly different. This change the refraction index at its own frequency. This change the refraction index at other frequency. This created new frequency. Okay, so and all of them are part of the Curry effect. Okay, a part of the Curry effect. Next, on Wednesday, okay, the next lecture will prove that all these terms, cell-phase modulation, cross-phase modulation, 4-wave mixing, okay, all these terms, when you add them together and then you do Fourier transform, it will give you this term. Okay, it will give you the refraction index at certain time is modulated by the intensity of light at that time. Okay, so in a lot of literature and papers, you see that when people refer to Curry effect, they are referring to this relationship, okay, this effect, okay, where your refraction index at a certain time is modulated by its intensity, and inside Curry effect, there will be three different phenomenon that happen on the frequency domain, okay, cell-phase modulation, cross-phase modulation, 4-wave mixing, and by tweaking the experimental condition, sometimes one of the effect would be dominant than the others, and then people focus on saying, okay, 4-wave mixing. I do experiment to verify 4-wave mixing in this specific setting. You will know that, okay, 4-wave mixing is actually coming from the same Curry effect. Okay. Any questions? Okay. And so a final touch here, I'm not going to go through the math. I think you guys can get the idea, is that in the process of generating new wave, new frequency, does the phase matching condition matters? Right? Does the phase matching condition matters? And of course, by looking at these K factors here, of course it matters, right? You can kind of see. You can kind of see that, okay, you have K mu on the left-hand side, and then on the right-hand side is K mu 1 plus K mu 2 minus K mu 3. Okay, if K mu equal to this, then you have a phase matched condition. And on the note, let me just emphasize the critical difference of phase matching condition in Curry effect, okay, third order Curry effect, compared with the harmonic generation, which we previously studied. Right? The critical difference here is that all these frequencies, they're very close to each other, right? As we say here, okay. Okay, mu 1, mu 2, mu 3, right? They're all very close to each other. In most experiment, for example, bulk optics experiment, the difference can be a few hundred megahertz, okay? And the optical frequency is a few hundred terahertz. So it's 10 to the 1 per million change, okay, in terms of frequency. And in more like smaller structure, for example, the microresonator, integrated photonics, the difference is also only just a few tens of gigahertz or a few hundred gigahertz, still very small compared with harmonic generation. So when dealing with the phase matching condition here, one thing you can do, as we know that K mu is equal to M mu omega mu C, right? So something you can do here is when you try to calculate n omega, right, the refraction index at frequency omega, you can take advantage of the Taylor expansion, right? You can choose, for example, okay, this is the omega naught, right? This is the center frequency of my system, and then I can do Taylor expansion around it. Okay, and then this is right, you can do Taylor expansion around it, and then this will give you the phase matching condition, and it is much more pleasant, okay, to work with compared with the harmonic generation. And later, okay, I'm not going into very detail here because later we will see that when doing the Fourier transform, okay, from frequency domain to time domain, you will see that this dispersion term can again become a very simple and elegant term. And so far, okay, nowadays, okay, about the latest research, controlling dispersion is still a very active research area. For example, if you go by optical fiber, okay, that's kind of developed 20 or 30 years ago, you will see that the optical fiber was designed for 1550 nanometer, but usually you have a slash also 1310 nanometer. Okay, the reason that it works at dual band is at 1310 nanometer. Why people actually care about that band is that your fiber actually has zero dispersion. That means the refraction index around 1310 nanometer, okay, is almost constant. Okay, and the same, okay, is happening here at the integrated photonic research. Okay, nowadays people are still applying a lot of method try to make the dispersion either very large, very small, or zero. Okay, you can make it like anonymous, meaning that the n omega. Well, we don't have to go into here. Okay, we'll discuss this later. Okay, anyway, that is kind of all of today. And if you are interested in